right. I think we're recording, so we shall begin. Welcome to yet another meeting of ENGR-1330, Computational Thinning and Data Science. And welcome to the less than 10 people that have showed up again. So you obviously got the message that the recordings fail, so it was good of you to be here. Those who were here last time, y'all lucked out. Today is the 14th. And I would normally call roll, but I think I know everybody's name. So you're Avery, and you are Rory. McGuire, Jerry's cousin. Mateo. Okay, just gotta find your last name. There you are. Oh, this is embarrassing. I should know who you are. Catherine in the back. Elizabeth. And do that hard. Rats. I forgot your name. What's your name? Yes. Jeanette. Oh, okay. So one of the easy things of professoring is I got a list of names, and there's like 7 or 8 women in this class. So I was looking for a woman's name, and I couldn't see yours. All the other ones were accounted for. Is that Mark Riddle?
Yes, sir.
It is. And the other gentleman up there by the door, Stephen and Alan?
Yes, sir.
Cool. All right, we will get started. You all have had your roll taken. 1, 2, 3, 4, 5, 6, 7, 8. 10 counting the sign interpreters. So we have a quorum. Today's lesson is folded up. So today we're moving on to some new concepts. We're going to discuss cause and effect, or causality, as it applies to data science and science in general. A little exploration of randomness, probability, and correlation. So there's a lot in today's lesson. So parts of it will go fast. Parts will involve our friend probability, which most people I've observed over the years have decided that it's almost like chemistry and therefore not worth trying to even understand. It's really not that hard if you just accept it as a type of arithmetic and don't get all messed up with the jargon. Okay, so here is our notes. Causality, correlation, randomness, and probability. And those 4 things don't normally go together. I just had to throw them somewhere, so I put them in this bucket called a Jupyter Notebook and then shook it up, and we will go from there. So our objectives today are to at least introduce the fundamental concepts involved in causality and the difference between cause and correlation. And then we're going to do some simulation stuff. We're actually going to teach you all how to gamble on the computer. Not how to log into a gambling website and turn your money into somebody else's, but the concepts of gaming. And I assure you can program your phone to do this, so next time you're in Las Vegas, you'll be able to hack into the slot machine and have it deliver you money, and then the big dudes with the black glasses, as they start lurching their way over to you, grab your money and go. And since they don't pay real money anymore, you're going to get... It's going to be like Ocean's 11 out in the back room. And hopefully the person who's assigned to clobber you is a good friend, so they don't actually hurt you too much. So first, what is causality? So I have a long-winded pseudo-definition. I'll read some of it, and I'll stop and let you all read on your own in your own time. So causality, in its most long-winded way of defining it, it's the relationship between cause and effect. The notion of causality does not have a uniform definition in science. That's awful damn convenient for scientists. And it's studied using philosophy and statistics. From the perspective of physics, they've at least decided that they needed a definition. It's believed that causality cannot occur between an effect and an event if they're not on the same light cone as the event, which is a complicated way of saying if Captain Kirk yesterday had blown up on his little space flight, that only would have happened if he actually got on. It had to be in the timeline of that occurring. That has some cosmological impacts, but not so much for our case. In terms of Star Trek kind of stuff, all that stuff, Spock coming back from the future to deal with the Romulan dude who had the really bad tattoos on his face, who was really mad at the universe because his tattoo artist really screwed up his face. That can't happen. The physics principles of causality, as we understand them, forbid that type of time travel. If you get into time travel and you decide this engineering and computer science gig isn't for you, here's a couple of journal articles you might want to read that discuss something called a closed time loop in very philosophical sense. If you have some literary skills, this could be a really long, productive science fiction genre for you to engage in and get rich. And remember, I told you here first. The second article I think is really cool because it was actually written by an undergraduate student, which is quite rare that something like that appears in a journal article. So obviously the undergraduate student was somewhat gifted. Maybe they stayed awake in high school and were encouraged by probably family members to go ahead and do it. So they're basically smarter than their professors. And that's probably true throughout this campus. Both concepts theoretically support this notion of timeline. So that's a big, broad philosophical picture of causality. Let's look at a more mundane one, because I actually did the arithmetic just before I came over here. And let me see what I have that I can drop that won't damage too much. Okay, so this is a red piece of chalk. I'm going to stand here. I can stand here and hold it until I pass out from exhaustion. What if I let go of it? What's going to happen? She thinks it's going to fall. What do you think, Rory? You think it's going to fall, Mateo? Yeah. Fall or stay in the air? It's a question. Okay. Elizabeth? Fall? Catherine?
I think it's going to float.
She thinks it's going to float. Okay, so we have one contrarian. Stephen? Oh, two contrarians. Mark?
Fall.
Fall. Okay, so 2 out of 10 of you think this will float. The rest of you think it's going to fall. Those who went in the fall camp, I agree with you. So was it instantaneous leaving my fingers till it got to the floor? You watch my fingers open, and then a fraction of a second later, you heard it hit. So we could do our engineering stuff. Here's the floor. I chose red because it's got pools of blood because we're now dropping stuff and breaking it. And my chalk was located here. One thing that we could do is measure the distance or stipulate the distance from the chalk to the floor. Now we need a data model because that's the whole point of this class. And the data model I propose is time, which is the time it takes to move from here down to the floor. I gotta get my squares and square roots right. Yeah. And we've already examined last time in lab ways we could address that if we had measurements of time in cap H. So suppose we come up with values for beta 0 and beta 1. So now we have our data model. We want to predict what's going to happen if instead of H being this distance, it's a different distance. It's down here. We'll call it little h, mini h. So the time from when I release it to when you hear it hit, does it go up or down? Well, let's test that conjecture. Okay, so I'm dropping it from the same height. I've just moved the floor up. So that's roughly half the distance. There was time, but it seems like it's shorter than that amount of time. So sure enough, our data model is a good model of this physical process. And every time I let go of the chalk in this room, in this location, it's going to fall. What causes that to happen? Go ahead and say it out loud. So it's just in gravity. Yeah, I like to call it gravity with a B because it's grabbing the thing and it's pulling it towards the center of the earth. So the cause of the effect, which in our case is the time from release to making the noise, we all know that as gravity. Now there's no data science there per se, but that's clearly cause. So if I were to move to another celestial body, say the moon, that period of time for the same height, would it be the same or would it be different? Different. Why?
Not as much gravity.
Not as much gravity. So in our data model, what would change in that instance? Probably the beta 1. That's the constant that somehow is reflecting the relationship between time and height. That's correct. So that is causation. There's another concept called correlation, which I call causality's mimic. And we'll look at a diagram. It looks better on my screen. I think we'll be able to get the point on what correlation is. So before we move to correlation, causality is an answer to the question, why? Because. So in the literary world, if you see the word because, there should be a clause preceding that somehow postulates a variation of the question why, and then because is the cause of the why. And I pontificate here, don't use the word since because that has to do with time, and that's a good way to do your scientific writing incorrectly. Since we let go of the deal, it fell. It's because we let go, gravity pulled it down and it fell. So here's a chart of some numbers on the left-right axis and other numbers on the up-down axis. And actually, let's go ahead and make it a little bit bigger so you can see it. Almost no effect. Of course not. Is this chart properly built according to our graphics standards? So what are the things that you check? Does it have a title? Are the axes labeled? Does it have a legend? I'm getting a no from Elizabeth. What's missing? The left-right axis should say years or something. You're right. The other thing is missing, there's no title. But for the most part, this is an acceptable graphic. And so we have some dots following a path. They're getting further away from the left-right axis as we move to the right. Some of the dots in the line through them are blue, some are orange. In the absence of the legend, could you really tell the two lines apart? I mean, yeah, you can, but they're kind of conveying the same information. So it says the blue line is the total number of lawyers nationally, and the orange line is the money spent on pets. Well, clearly based on this chart, if I wanted to predict the money spent on pets in any year of that chart, it'd be pretty easy. Count the number of lawyers, multiply by 1 point something, and I have the money spent on pets. So does the existence of lawyers cause pets? No, that doesn't make any sense. There is no cause. Does the existence of pets cause lawyers? Possibly true. But those have no direct causal relationship to one another, although the two variables are very well correlated. And what that correlation is telling us in a philosophical sense is probably the general socioeconomic conditions that adapt for lawyers goes throughout whatever that society is, and people have more disposable income, and they dispose of that on their companion animals. And we're talking companion pets here. I'm assuming this does not refer to those pets that are just meat that haven't been cooked yet. Those are called livestock. It's a different concept. So if you were to believe that there was causality, a very dangerous thing would be to go take up Shakespeare's statement. And so first we kill all the lawyers, and says, well, that means all the pets are going to die. I mean, that's going to be awful. The pets didn't ask to be created by lawyers. They're just doing what pets do. So that silly story is correlation. So correlation in and of itself does not imply cause. Obviously, if there is a cause-effect, it's likely that the two things are going to have a strong correlation. In fact, it has to be. Let's go some little more scientific ideas. So there's two chemicals that are common in groundwater. One's called atrazine. You don't want to drink it. It's bad for you. It'll make you grow spare parts and then burp and die. The other one is nitrate. That's not as bad for you. All that does is make your babies die. And so they get measured in wells over a several county area. And all the morbidity is just to mostly keep you entertained here. So suppose we collect a sample of these groundwaters. So we go down to a well and we tie a rope around the smallest baby. We put a bucket in its hand, lower it, pull it up. We have a groundwater sample. We could dispense with the baby part and just tie it to the bottle, but it's more fun in your mind right now to think of a little critter down there going. So you pull it up and we measure the concentrations, and we discover that when we measure the concentrations in each of these samples, every time the atrazine concentrations increase relative to some other sample, turns out the nitrate ones do too. And a data science question would be, how strong is that association? How prevalent is that? Is that always the case, or is it just in most of the case? Or is it as strong as I can multiply the atrazine by a constant and that gives me the nitrate, or vice versa? Does atrazine cause nitrate? I imagine most of you are not chemists or chemical engineers. One of them is an amine, the other one is an inorganic, so no. They're chemically in the wrong parts of the periodic table of elements. How would those things be together in a groundwater sample? And that again, the data scientist would have to ask some deeper domain knowledge questions. Well, atrazine is an agricultural chemical that's used as it's a type of pesticide. Nitrate is the result of anhydrous ammonia injection to make things grow. So we don't get big old potatoes just by the miracle of nature. We inject them full of chemistry so that they're big old potatoes. So it would make sense that the same process that fertilizes food crops would also possibly use pesticide to protect those crops so they can make it to harvest. So it's not unreasonable for those two particular chemicals to track one another in an agricultural environment. And so we might want to summarize how that goes. A similar thought, it's actually kind of poignant today. So the streams that drain the Sierra Nevada mountains in California usually receive less precipitation in November than in other months. What month is this month? October. When's November happen? Next month. California is on fire right now, and they're in the midst of a drought. This probably really concerns them in real world, because you would hope that the rains would come and put the fires out, and you go, okay, finally we can do Christmas, and then figure out how to get all of our economy back running. Probably ain't going to happen. But you might want to ask the question, well, is November that's coming up next month, is it likely to have less rain than we saw November 20 years ago or not? And again, that's a correlation type question. So we know that the November rains are lesser than the other months. We don't know if the November rains over the last 20 or 30 years have been changing. Actually, there's probably data for that. And again, we want to assess how would we even test that conjecture. In both cases, we get back to our measures of how joint variables change, and one class of such measures are called correlation coefficients. And in addition to the fact that there is an association, is how strong that association. The Pett-Lawyer association was really strong. You could have changed the colors and disappeared the legend, and either one of those would have been good enough to predict Petts or lawyers, as long as you're using the correct axes. Our causality with our chalk dropping is extremely strong. Our correlation with chalk dropping is extremely strong. In fact, if we had a good stopwatch and a good meter stick, it would be probably as close to exact as we can get in humanly thinkable things. So what are some of the measures? There's a bunch. I'm going to introduce one to you right now called covariance. And covariance is a measure of the joint variability of two variables. In the words up there it says random variables. They don't have to be random, although covariance isn't very interesting for non-random stuff. And the formula is shown right up there. Formula just assumes that the variable pairs x and y in that formula, that for each x there's a y. So think of it as dots on a scatter chart. And we're simply going to compute the mean value of all the x dots. That's easy enough to do. If it's in a pandas data frame, how would you do it? Data frame name dot, four-letter word, begins with letter M, ends with the letter N, and has two vowels in it. Yeah. Panda data frame name dot mean, and I guess you would have to identify the key, the column in the data frame that you want the mean value of. Okay, so we can do that, and then we can subtract every element of the column, subtract the mean from it, and add all those up. We can do the same for the y column. Multiply those two, divide by however many things there are, minus 1. The minus 1 is a consequence of statisticians, and that's over in the math department. We don't give a crap right now, but you will when you take the class. And the result of that is a numerical value that's called the covariance. In this case, the notation is the covariance of x and y. We also could do the covariance of x and x, but we already know that as a different name. Somebody speculated, guess what it means. Take the word co off, you have it. So, yeah, if we do the covariance of x and x, we actually calculate it as variance, which is the square of its standard deviation. Covariance of y and y, same story. And then the covariance of y and x, they're symmetric. All that is switching the order of those multiplications, and in this case, the multiplication is nice and transitive. So Really what covariance is trying to show is a picture like this. And this is labeled correlation, and we'll explain that in a second. But as x varies, if y varies in the same direction, we would call that, the value of covariance would be a positive number and probably quite large. If the opposite's true, it would be kind of trending downward that way, and that would produce a relatively small negative number. I was looking up here to make sure nothing is squared so that we can have positive and negative numbers. And then if we have the case where regardless of what x is, it gives us no meaningful information on the value of y. The middle one, which is labeled up there as 0 correlation, that would be a covariance that's relatively small. Now, covariance in and of itself, the sign is valuable in helping understand these relationships, but the magnitude, how big the number is generally not terribly helpful because the number themselves depends on the magnitude of the things. However, if we normalize it, which is a fancy way of making things stay between -1 and 1, that is called a correlation coefficient. And that has value because not only does the sign give us information, the numerical value, how big it is, how close or far from 1 it is, gives us information. And there's the correlation coefficient formula. That one is for something called Pearson's R. Like all things in the world of arithmetic and engineering and data science, there's at least 1,000 ways to do something. This one is by far the most, I use the word popular. It's as if you go to the beach and they go, yeah, get a Pearson's correlation coefficient. You want to get away from that beach really fast. But it's the one that's certainly most commonly used in the literature, and it's not too difficult to compute. It's using funny notation here, so it looks difficult to compute, but that's just job security for statisticians. It's just saying count how many things there are, sum up the product of each thing, the x and the y, subtract from that sum all the x's summed up, times all the y's summed up, and then divide that whole thing by how many things there are, sum of x squared minus the sum of x's quantity squared, times how many things there are, times the sum of y squared minus the sum of y's quantity squared. Put all that together and stick it in a variable named r. It's the preferred correlation coefficient of pirates everywhere, r. And the value in a correlation coefficient ranges between -1 and 1. And the sign of it tells us whether there's positive correlation or negative correlation. And how close to 1 or -1 it is gives an indication of the strength of the linear component of the relationship. So the picture up there shows a cloud of dots that's going from the lower left-hand corner to the upper right-hand corner, and then there's this blue line passed through it, not unlike the blue lines we passed through the red dots in lab last time. And it says that the correlation coefficient is 0.4. So 0.4 is not 0. There's in the pictures, there's clearly some correlation, but 0.4 is not as good as 1.0. And then we have the same story here, only now it's -0.4. So -0.4 is not -1. So there is the potential for better correlation, but it's the best we can do with those black dots. And negative correlation simply means is the horizontal variable gets bigger, the up-down variable gets smaller. And then there's the cloud that looks almost like a rectangular sampling of the whole graphic space. And there's this, for all practical purposes, a horizontal line drawn through it, and that has a correlation coefficient of 0. And that implies to us that knowing the value of x gives us no information on the value of y.
you might as well just use the mean value of y as the estimate, because regardless of what x you choose, that blue line's suggesting that we can't learn anything about y. And that's the essence of a correlation coefficient. So these two non-zero correlation coefficients, they don't imply causality. But if you're an online business and your horizontal axis might be the day of the week, and the vertical axis might be the number of sales, you want to promote your stuff later in the week. Whether there's causality or not is irrelevant. Correlation is a good predictor of ways to make money. And there are two huge industries that you're all familiar with, probably have interacted with, that have built their business on that. One of them is named after a little teeny river in South America, and recently took the character Captain Kirk into real space the first time. Of course, he was pretty cool because he'd been in outer space without ever having to use a ship. The other one has become a verb in our language. So what do you do when you don't know anything? You Google it. Yeah, both those companies have built their business model on correlation coefficient. Now, I dare say Google probably uses something a little bit more sophisticated than Pearson's correlation coefficient, and probably more than just two variables. And when that doesn't work, they send their little Google spies into your room when you're sleeping and steal every bit of knowledge that's laying in your room. So remember to tape up your video cameras. Let's look at a simple example using numbers and stuff that we probably can wrap our brains around to illustrate the concept of association and correlation. Let's consider a table of speeds and times from some experimental observations. So I believe we had something like this, at least on a recent lab or on exam one. If not on exam one, it's coming up on an exam. So the left column is time in seconds. The right column is speed in meters per second. And so just looking at that, what's the smallest speed you can observe in a data set? 0. That corresponds to what time? Oh, so that's how fast my chalk is dropping before I let it go. And then 10 seconds later, my chalk is dropping at 121 meters per second. Is that fast? Yeah. If your body were to drop that fast and encounter a sudden stop, such as the Earth, your contents would be spread out over a larger area than they currently are. Upside is that couldn't possibly hurt. So let's go ahead and load this into a data frame and explore the data. So we would load the necessary packages. So we're going to import NumPy, pandas, and then a new package, statistics. Terrible name for a package because people see that word and it scares them. The only thing that would be even scarier would be the biochemistry package, unless you're into that. And then from the matplot library, we'll pull out Python plot and we'll name it PLT. So this as structure, who recalls what that is? Or somebody play along and tell me what the as. Yeah, I'm renaming the package. So instead of having to type numpy dot and whatever the method is, I can do np dot and whatever the method is. And this is pretty common if you search out the mighty GoogleNet and look for code to borrow, and then cite, and then modify and use. You'll see this almost exclusively. So whoever did this first should be very proud of themselves because all the code thieves on the planet have totally adopted that. And I'm kind of arrogant, and sometimes I will go to the trouble of actually doing it the way it was intended, and will not do the aliasing, and I have to go fix a lot of things. So I would have to replace PD with pandas. Okay, anyway, good. Let's continue. So we'll create a data frame of time and speed. So these first two highlighted lines right there, time and speed, are what kind of structures? Those are lists. Very good. And they become a data frame when we tell it to be a data frame. And in this case, the keyword of the column is time, and it's going to contain the time list, and the other keyword is speed. It's contain the speed list. You wouldn't necessarily have to create the data frame this way. You could actually do it all in one call. And now we'll go look at the contents of data. And naturally, it can't find my packages. Oh, you piece of... Why does it have to do that? This will be good. This is how you have to install stuff when it is disobedient. What is my password? Oh, okay, I know what's wrong. I'm on the wrong server. That was stupid. All right, let's try that again. There we are. Much better. Okay, so now we're caught back up. And now we'll explore the data. If you remember in our pandas lessons, we learned a describe function. And so if we invoke the describe, it's actually a method, the describe method, it tells us that how many entries of time are there. Can you read the screen, I guess is what I'm asking. Yeah, okay, everyone's mouthing 11, that's correct. What's the mean value of time? 5. Mean value of speed. Those don't particularly have much utility in this particular instance, but they're returned. And it gives us standard deviation, minimum, maximum values, and the 3 quantiles, the 25th, 50th, and 75th percentile. Since these are data that, for all we know, are causal, in other words, there's a cause-effect thing, those quantiles aren't necessarily very useful. Let's go ahead and find what the variance of time is and the variance of speed. And we'll use the statistics package because basically it's going to run that covariance function for us, and we don't have to be doing for I equals length and doing the time and squaring stuff. Somebody who's into that has spent a lot more effort at doing that. And so we'll run that, and we get back that the variance of time is 11, and the variance of speed, good, so we have a little result here, is 1697. And variance of something doesn't have any units. So the variance of time would have units of time squared, and the variance of speed would have meters squared per second squared, which are weird units. If you recall what the covariance or the variance does, could somebody speculate what the square root of 11 is by just looking what's up on that screen? I argue that it's probably 3.316625. And that's because the standard deviation squared, by definition, is the variance. Also means that the square root of 1,697.77598 is 41.204. We could test that, but that's unimportant at this point. Now to find the covariance, it's extremely difficult when it's in a data frame. The name of the data frame, the method and the dot identifier to find the method, and then the very difficult to remember name, COV, covariance. Run that. and it gives us the covariance matrix back. So you notice there's a diagonal entry. The diagonal entry will always be the variance of the variable pair, because time, if it covaries with itself, is a variance. Speed, if it covaries with itself, is a variance. And then the off-diagonal terms are symmetric. So the covariance of speed and time is 137, and the covariance of time and speed is also 137. And we can have more than just two variable pairs. There could be a lot more than just two. Let's suppose we want to find the correlation coefficient. That's also quite difficult. We use data and then the method identifier and then the keyword CORR for correlation. And we actually have to specify the method because naturally there's a dozen in there. And I don't know what the default one is, so I selected Pearson. And it now gives us a correlation coefficient. So, we would know correlation coefficients. Are the values between -1 and 1? That'd be a yes. Are the variables correlated with themselves perfectly? Yes. A variable correlated with itself should have a correlation coefficient of 1. And in fact, that's actually a diagnostic when you do your own analyses. So if time and speed, for instance, had a computed correlation coefficient of 1, I would be concerned that I'd accidentally correlated the wrong columns. Because with real data, we should never get correlation coefficients of 1. We can get darn close. But if we get a 1, it probably is a data entry error on our part. Now, is time and speed correlated with one another? And that's the question is, are they close to 1 or -1 or close to 0? They're close to 1, so they are strongly correlated with one another, positive or negative correlation. So as time gets bigger, what do you expect speed to do? Good. So that's all that's meant by association. And these values suggest that time's a good estimator of time, which it should be, and it's also a pretty good estimator of speed. I'm using the symbol U. And if we wanted to, we could hack together a usable linear model, which structurally will look something like this, except not with the squared part. Well, we're going to replace our intercept with the mean value of speed, and then we're going to replace our slope with the ratio of covariances. So the covariance of speed versus time over the covariance of time versus time, that is to scale the estimator correctly. So that's just a linear model. Those are beta 0 and beta 1. But you all remember from lab last time that it really quickly became a pain in the you choose the body part to start guessing. So here's our first attempt to systematize it. I don't recommend you use this outside this class, but this is leading towards some other things in the near future. So we'll import our plotting package, although because we have pandas, there's built-in stuff. And now we're going to create a data model, and it's going to take the mean value of speed, that's our beta 0, and it's going to take time minus its mean, and then it's going to multiply by those covariance ratios, and then we're going to plot it. And there's our data model. No trial and error. Obviously not perfect. But is that a bad data model? Let me rephrase that. Can you think of worse data models? Yeah, we could have a horizontal blue line at -500. Be a really crummy predictor. We could have a vertical blue line at 3, also a crummy predictor. Or we could have this line right here. And if we wanted to predict what the speed would be at, say, 11 seconds, we certainly could do it. It wouldn't. It's not picking up the curvature, so it would be wrong. We know that ahead of time. But we actually know some additional information. We know it would be wrong by being too high or too low? Too low. That's useful bit of information, at least in engineering and in arguing speeding tickets. If you know that the radar is reading too high and you can somehow demonstrably prove that to a jury, after you've expended about $100,000, you can get out of your $200 speeding ticket, which financially is not a good deal, but it would sure feel good just once. Okay, so the implications of all this is most research questions are attempts to explain cause and effect. In experimental research, often it's somewhat easy because we can construct experiments that detect that. In data science experiments, we don't really construct experiments. We're using databases, and we're trying to infer cause and effect from those. So there's some added bonus challenges. In the case of experimental, we can design the experiment so that the compound of interest is applied to one group of victims, subjects, and a fake thing is applied to another group of subjects. So we're all living through a COVID era, and they put in these squirty things on our arm to make us live longer. So part of the testing of that was the safety testing. So they would take probably more than 100, a couple thousand people, and say, okay, you're one group, you're the other group. You guys wear green t-shirts, you wear red t-shirts. And all the green t-shirts, you give them a COVID vaccine. One of the ones you just pull out of the freezer, pop it in the microwave to thaw it so it will go in, shoot them. The other group, you give them morphine or something that will make their lives happy for a few hours. Then you count how many of each group dies in the next 24 hours. And if it's not too many, or if the amount of deaths is about the same, you can reasonably conclude, okay, my treatment, my vaccine, as compared to the control, I said morphine, but I probably just use normal saline, at the same death rate. Therefore, that product is safe, because we've already established it's okay to inject salt water into people. And the next step of that is to do the same thing again, but now you expose the people that got the treatment to all sorts of viruses. You just go down to the virus store. It's right next to Home Depot, across from Babies R Us. And you put a thing on the mask, and you squirt virus into them, and then you watch them for a few days and see if they get sick and croak. Okay, that is a grotesque bastardization of medical research, but that is experimental research with control and treatment. And what we're evaluating in that, we don't necessarily know that the treatment caused the viruses not to kill people, but there's probably a pretty strong correlation. And so we're after that correlation coefficient. We probably want positive correlation coefficient, and that's how we use it to tell if the treatment is worth it or not. And if it turns out that this waving garlic over them has the same overall performance, or get those really cool nose masks and you stuff the garlic in it, like they did back in the olden days when bubonic plague roamed the earth. In data science approach, we don't necessarily have that luxury, and so often we have to start with observing an association, cats and lawyers, and all we can do is try to come up with a relationship between the treatment and the outcome, which is called an association. We can measure the strength by a correlation coefficient. Then, once we had done that, we would perform a more elaborate analysis in an attempt to establish causality. So one approach is to control all variables other than the suspect variables for which any meaningful process is essentially possible. And that's fairly hard to do and outside the scope of this class, but that's one thing that is commonly done in data science. The other one is to try to establish randomized control studies. And that you would take a sample from the population, either live volunteers to test vaccines or data from a huge database, randomly assign proportions of that sample to either the control group or the treatment group, green shirts or red shirts. I guess I should use blue shirts and red shirts because then I can go back to the whole red pill thing that I used earlier. Expose the two groups identically, except the control group gets a false treatment. And then compare the responses of the two groups. If they're the same, then there's no evidence that the treatment variable caused a response. So if they're the same, what would you expect the correlation coefficient to be in that comparison? It was the blue horizontal line correlation coefficient. Yeah, pretty close to 0. Probably wouldn't be exactly 0 because the gods of data are evil, and they always give you non-zero stuff just to screw with you. But if there was a positive correlation coefficient, probably bigger than 0.5, or a negative one smaller than minus 0.5, you would conclude that there is some evidence of causality and then pursue that particular variable further. So that's the essence of correlation. Let's look at this picture here. I'm good on time. I may have to actually just speed up. So this is a plot from a Texas database. Every week, every state reports to the Control Data Centers for Disease Control certain special reportable data, and it all gets tabulated and summarized in something called the MMWR, which is an acronym for Morbidity and Mortality Weekly Report. Or maybe the mortality comes first. I'm not sure which. And so this is influenza reported for 2009, 2010. On the horizontal axis, that's the left-right axis, what's the variable? It's a date, yeah, it's a particular week. On the left up-down axis, it's number of positive tests. On the right axis is a percentage. We're not going to worry about the right axis. And ignore the colors. Those vertical bars, what kind of plot is that? It's not an antihistamine, it's a not antihist, but histogram. Thank you. It's a histogram. So the height of the bars is conveying a numerical value on either of the axes. Ignore the different colors. This happens to be a cumulative histogram, so the bars are stacked on top of each other. And the different colors represent different types of influenza virus, whether it's H2N2, H1N2, or H1N1. We won't worry about that. We'll just worry about the flu. So if we go look around August, which is right here, there's non-zero flu reports. So yeah, that's that late summer flu that everybody gets. And then the next month is September. What happens in September with regards to flu? It went way up. What happens in September with regards to school-aged children? They go back to school. Well, there you go. It's clear that going to school is what causes the flu. So if we just schooled at home everybody by internet, the flu would go down. The subtle flaw in that is look around January and February. What happens in January and February with regards to school children? You all used to be them not that long ago. Technically you are still right now, but you're not children anymore. In January and February, you go back to school. Mom and Dad would go, oh, thank God they're out of the house again. So, but there's no spike in flu relative to the first one. So clearly school causes flu, but only school in the fall. So if we would just quit those 4 months of school, it'd be great. There'd be much less flu. Everybody'd be happier. We'd have to educate our society using only 4 months of the year instead of the whopping 8 that we do. And so you could use a chart like that to maybe attempt to answer questions like this. You know, does going to school cause flu? Probably not. Excuse me, that's probably a good place to pick it up. Does flu cause school attendance? Absolutely not. Getting people sick isn't going to make them go to school to get better. It's not like going to work so that you can rest up for your vacation. Does going to school contribute to the spread of flu? Now that's a data science question we could attempt to test. If we had data on homeschooling and flu compared to in-school and flu, we could test that conjecture, again by a correlation coefficient. Does the spread of flu contribute to school attendance? Doubtful. Are there other variables? Well, yeah. Which school season is it? Is it the fall or the spring? What's the temperature in that particular year? So there's a lot of other things that could influence this behavior. Those other things are called confounding factors, which is a really cool word for everything else that we can't explain. And the confounding factors appear when there are actually contributing variables that we're completely unaware of. They also occur when we have variables that are somehow correlated to one another. So our flu predictor variable might be correlated to temperature and school attendance. And it might be that temperature and school attendance have a strong correlation, and in data science analysis, we have to remove that. And we're not going to look at that today. This is just background. Okay, let's move on and start doing some gambling. To establish presumptive causality in experiments, we need the ability to randomize things. And this will be, for those of you that are here, this will be the best part of today. When you take your probability and statistics class, if you haven't yet, some of you might actually hate it, find it incredibly confusing. Easiest way to think of it is that all that class is a bunch of people got together in a room with computers before computers were invented, so they used Reese's monkeys, and they would feed them Reese's pieces to keep them motivated. And they threw dice a lot, over and over again. They kept track of it, and that's how they built these probability and statistics models. We have computers, so we can let it throw the dice for us. So we need something that can at least mimic a fair dice, if there is such a thing. So we're going to use Python to make some pseudo-random choices. There's a lot of built-in functions in NumPy under the random submodule. There's a lot of similar stuff in Pandas. There's similar stuff in statistics. There's similar stuff in Skippy. There's a whole bunch of ways to generate random numbers, and they're all valid. So the example we're going to go through here is NumPy random choice, and then give it an array name. So here's what we want to do. We're going to have an array name something, and what random choice is going to do is it will pick from that array some element. Let's say the array has 3 elements in it. So either pick element 0, 1, or 2, whatever is contained there. And it'll set that aside. And if we do it again, it'll pick from those 3. So it does something called sampling with replacement. So let's go ahead and produce an array called 2 groups. And in that group, we're going to have an element called treatment and an element called control. And then we're going to take from that array, named 2 groups, 1 item. So if it only has 2 things in it, what are the 2 possibilities that I can get with a single sampling from it? Either control or treatment. So we'll go ahead and run that. And that time we got control back. I'll make sure this is actually working. That's disturbing. I shouldn't keep getting the same thing. Well, we'll pretend it's working. my list. This has got to be the same syntax. Okay, we'll do it that way. So I think I got different numbers back, which is what different values back. So we could use that to, for example, we could build a die. A die, those little square things that they have in Las Vegas that you ship in the movie, so that they always turn up the number that you want when you press the button on your phone. And so on that die, we'll have a number 1, 2, 3, 4, 5, and 6. And we will sample from that die to represent a single roll of the die and see what we get. So that time I rolled the die, I got a 5 back. If I roll it again, and I got another 5, and if I rolled it again and got another 5, how many 5s in a row would you all let me do before one of you reaches into your shirt and takes out a revolver and plugs it? You're not a very fun person to gamble with. But probably 3 or 4 in a row, it'd be time for me to be looking for that back door and say, oh, I got to get up and go use the restroom. I'll be back in a minute. Let me take all this money. Yeah. Okay. So what you want to do when you're doing sneaky gambling is what you would really like to be able to do is to modify how the die performs. So now I've just made it so 3 of the 6 choices are a 5. So I would expect it to come up 5 somewhat frequently. And at that point, you would go ahead and get your pistol out and change my thinking. There we go. We're back to a regular die. I'm not encouraging that you all play dice and gamble and shoot one another. Because you got to remember to have a shovel when you do that. Okay, let's now roll what is a fair die 6 times. So I rolled it once, I got a 3, then a 1, then a 5, then a 6, then a 3, then a 4. I got 2 3s. It would have been nice if I could have gotten one of each numbers. If we did this enough times, we would get about the same relative frequency of each of the numbers. And we can also do multiple rolls in a single die, and we get back a list. So there's our first tool in randomizing. And so now if we wanted to ask questions about throwing dice, we can either read our probability book, which is written in gibberish and language we can't understand, because that's what the people in the math building do. They need better air conditioning. Or we can throw die over and over again with a computer to learn how it should behave, and then use that to help make a decision of when or when not to shoot our other players. So I guess you can call that a game. Alternatively, it's called simulation. And that is the basis of a lot of modern probability and statistics. It's we simulate them on a computer in order to be able to make statements about the process of interest. In our case of control and treatment, we would use a tool like this to assign whether you get a red shirt or a green shirt. So now we're going to go ahead and make the game fun, because we're going to involve money. So let's create a game with the following rules. If the dice turns up a 1 or a 2, you lose $1. If a dice shows a 3 or a 4, it's a push. You don't lose anything. If the dice shows up a 5 or a 6, you gain $1. And to make this a proper gambling game, we'll do it just like we do in Las Vegas. you have to make your bet first before you get to roll the dice. So you'll take $1 out, you put it there in the bucket. There's a little black box next to it. You don't know what's in the box. You roll the die. If you get a losing roll, a little hand comes out of the box. It's almost Halloween. You know what I mean now. If you get the net gain of 0, nothing happens. The dollar stays there, and you can either play again or you can take it back. Or if you get the last case, the hand comes out of the box with $1 and deposits it on top of your $1. So that's the game we're going to play. A lot easier in real life, but here we'll do it in the computer. So let's just write a simple script. We're going to start with a wallet. This should be my Bitcoin lecture. If you can authenticate, this is how to steal all the Bitcoin in the world. So you start with a wallet, and we're going to have a function called place a bet. And the input to place a bet is a wallet, because to place a bet, you have to have money. That's the whole thing. You got to have money to make money. It's going to place a bet, and if what's in our wallet is 0, it tells you you don't have enough money, get the hell out of my casino. If you do have enough money, it takes that $1 out of your wallet, and now the bet is placed. Then we make a roll, and make a roll is also going to interact with whatever the current contents are out of the wallet. We roll a dice. If we get a 2 or less, it tells us you lose, and we lose the bet. If it's 4 or less, but still bigger than 2, draw, you can take your bet back. And lastly, if it's a 6, we win. And then here we'll do a single play. So we'll start with money in our wallet. We'll place a bet, we'll roll the dice, and then it will tell us what we have left. So this is a very simple game. The scripting is harder than describing it. What kinds of control structures do you see in these scripts? It's not sequential. It's not repetition. What was that other one? Begins with the letter S, has a few vowels in it. Actually, 3 of the 5 famous vowels. It has an E, an I, and an O in it. Selection. Is that what you said?
Close enough.
Close enough, okay. So yeah, this is all based on selection, and we're doing a single play, so we don't have any repetition. If we wrap that into a loop and played over and over again, then we would have repetition. There are elements of sequence in each of the subfunctions. So let's go ahead and play the game. So it looks like I'm starting with $1. This is not a good way to start your trip in Las Vegas. You should probably start there with more than $1 because you won't be hitchhiking home. So I had $1. I placed my bet. I rolled the die. I drew. I got my $1 back. Yay! That's an okay outcome. But let's say I'm a lazy gambler because I want to sit there and drink my free drinks while I'm gambling. So I'm now going to have my script go ahead and play the game for me. Now I feel like I'm doing a scene out of War Games, my generation of the movie. You all probably know that as a quaint little 1970s era silly movie with the Whopper. Not the burger, that was the name of the computer that predated Skynet, but tried to do the same thing. How about a nice game of chess? So we're going to start with $10. We're going to make one throw, and then we can modify how many throws to go. So the first one should produce almost the same result. So we started with $10. We lost. We now have 9. Let's see if we can play the game 10 times. So it's going to automatically replay the game, and it will quit. Actually, it won't quit when we run out of throws, but once our money goes negative, we already know that the big dudes in the casino are coming to escort us out. Oh. Well, I got lucky. I started with $10. I played 10 times, and I walked away with 11. And that usually doesn't happen when you guys go casino gambling. So don't let the computer deceive you. We can play more games with multiple gamblers and try to figure out what the best strategy is. But we're almost out of time for today, so I'm going to skip past that. So what I've just described to you is something called simulation. And there's important parts to simulation. You have to figure out what you want to simulate. Then you simulate a single instance of the thing. Then you figure out how to do repeated simulations. Finally, you code it up and then interpret the results. So we'll do one last example in about 2 minutes or less. This is important because it's actually on the lab, so at least I need to set up for the lab. So there was a game show called, I can't remember what the name of the game show was. It wasn't Monty Hall. It wasn't Dialing for Dollars. Let's Make a Deal. Who knows? But when I was younger, there was a show, and the actor was named Monty Hall. And they had this game, and they got near the end of it, and the contestants were shown 3 doors. And the actress name was Carol Merrill. Behind one of the doors that Carol Merrill is pointing to is a new Ferrari or car or something. And behind the other 2 are goats. And goats is just a metaphor for some chump prize. Maybe a t-shirt or a box of Velveeta cheese. And the contestants are asked, okay, so pick which door you think the car is behind. And so initially, when all the doors are closed, they pick a door, and then the game show host says, okay, you've chosen door number 2. Well, behind door number 3 is a block of Velveeta cheese, one of the goats. Do you want to change your choice? And the question, the data science question, is strategically, should you change your choice or not? I'll tell you right, the answer is yes, you should. That's the strategy. But let's, using classical probability thinking, see why that's so. When all 3 doors are closed, the chance of the car being behind any door you choose is 1 in 3. You have 1 in 3 chance of guessing the right door. When they open the door, that door now has 0 probability of having the car behind it. So one of the door that you didn't pick, its probability of having the car has gone from 1 in 3 to 2 in 3. It's simply the calculus of probability once that door has been revealed. So strategically, it's best to change doors. Most game show contestants didn't do that, and even though we can show strategically it's the better choice, there's one little secret thing that they never tell when they do these statistics examples, is that in game shows you only get to play it once. You don't get to play it 1,000 times like we're going to let our computer play for us to tell us that if we could do it over again 1,000 times, we'd come up with 600 cars instead of just 300 cars. And if you end up with 600 cars, you could open a car dealership and fail to pay your employees and make it into the Lubbock Avalanche Weekly News. So we'll start very much the same as before. In this case, we're creating a function called the other goat, which will return one of the other chump prizes, and then the actual game, and then our user guess. And notice we're using the random choice part. And I will blow through this quickly so we have time to go to lab. We get to do this again in lab. So I've loaded the game in. Now we want to make sure it's actually working. Sure enough, it does. If we have goat 1, goat 2, and car, and we look at the contents of the array, we get the 3 possibilities back. And now we're not going to play 10,000 games because that'll take. We'll play this game 1,000 times. And so we'll build a data frame, and what have we just done? We've just played the game 1,000 times. And now it's going to return the results. And so the first time the game was played, we made a guess, and the guess happened to be goat 1, but we never saw that. Then we were revealed goat number 2, and then what's left behind was the car. And now we're going to get the count of each item in the first and third column, and we'll make a grouped bar plot. And you can read the code on your own time. But the orange bars represent the case where we make our original guess and just stick with it. Go, no, Monty, I like my first guess. I think it's door number 1. So a third of those guesses, we get a car. Yay. Another third of those guesses, we get a Velveeta cheese block. That's goat type 1. And the last third of the guesses, we get a Dialing for Dollars t-shirt. That's goat type 2. So you don't really go away empty-handed, but nobody wants to go away with a chump prize. But if we had changed our guess, we'd come away with almost 700 cars and far fewer t-shirts and Velveeta cheese. In fact, probably we could put the Velveeta cheese and the t-shirts into the trunk of the cars and drive away, happy as can be, and open our own roadside stand in Venice Beach. So that's the power of simulation and using the computer to help us make inferences about data. Okay, we have to do lab in 15 minutes, so I will stop here. I'll try to pick this up on Tuesday, as well as Tuesday is descriptive statistics. That doesn't take the whole time, so we can finish this up on Tuesday. Thank you all for your attention and patience, and